So let's have some examples of vectors that uses the Cartesian coordinate systems. So in this example, we have two vectors A and B that are expressed in the rectangular coordinate system. So the first question is, what is the component of the vector A along the unit vector A sub y? So to answer that question, we simply get the dot product of the vector A with the unit vector A sub y. And that should give us a scalar answer. So this is a scalar. Now letter B, the magnitude of this expression. So this is a direct substitution. So the answer would be this one. And for the last requirement, a unit vector along this expression. So with the vector A plus twice of the vector B. So first we determine this vector. So it is direct substitution. So we will get this vector. And to get a unit vector that has the same direction as this, we simply take that vector and divide it by its magnitude. So that answer would be this. And we can even verify that this is a unit vector by computing for its magnitude, which we will get there to be unity. In this example, we have two vectors expressed as their components in a Cartesian coordinate system. So I will only answer B and C as A is simply a direct substitution problem. So to answer B, so we're asked to find the vector component of A along the direction of the unit vector A sub y. So to do this, we simply first get the component, the scalar component of A along the unit vector AY, and that is first we get the dot product A dot AY, and that will give us a scalar quantity that is in the direction of the vector AY, and simply associate the answer with the unit vector AY, and that would be the answer. And we notice that we will get here a 0. So what this means is that there is no component of AY that is along the unit vector AY. And the reason for that is that the vector A only has components along the x-axis and the z-axis. For letter C, to get a vector that is parallel to this vector, we simply get a unit vector, the unit vector of this resulting vector. So that would be the vector itself divided by the length of that vector. In this example, we have a vector field S. So vector fields are vectors that changes in magnitude and direction depending where are you in space, or depending what are your coordinates in space. So the first question is what is the vector at a point P with the coordinates 2, 4, and 3. And the second question is what is the unit vector that gives direction of S at that point. and C is what is the surface in space where the magnitude of the vector is 1. Okay, for the first requirement, what is the vector at the particular point? So the point is given. So all we need to do is substitute the value of the coordinates to the variables x, y, and z. So that would give us this answer. For the second question, what is the vector, the unit vector, which has the same direction as this one? So we simply copy the vector and divide that by the length of the vector or the magnitude of the vector. So we will get this one. So if we compute for the magnitude of this, that should give us an answer that is 1. Now for C, to get the surface where the magnitude of S is 1, so we simply get this value. So we have the x component of S plus the y component squared plus the z component squared, and get the square root of that and equate that to 1. So that would be this. And so simplifying the expression, this we will get an answer that looks like this, which is actually a sphere with a radius of 125 units and centered at x equals 1, y equals 2, and z equals -1. In this example, we have 3 points in space, A, B, and C. So we're asked to get the distance vector between points A and B, the distance vector between points A and C, the angle formed by the distance vectors RAB and RAC at point A, and the vector projection of the distance vector RAB on the vector RAC. So to answer this, first we need to, so I have here a drawing of the 3 points relative to the origin O. So this is just an arbitrary illustration, and it's not really 3D. So first we need to get the position vectors ROB, ROA, and ROC. So well, at least the two position vectors ROB and ROA. And then to answer the first question, to get the distance vector RAB, we simply get this one. So that will give us this answer. And for the distance vector RAC, we solve for this, and that should give us this answer. For the angle between the distance vector RAB and RAC at point A, so this angle here, um, first we need to get um, the dot product of the two unit the two distance vectors RAB and RAC and equate that to the meaning of the dot product, which is actually the product of their magnitudes times the cosine of the angle between the two vectors, so the smaller angle. And on the left side, we solve this by using the standard formula for computing for the dot product using the where the vectors are expressed in their coordinate system. So that would be the x components, the product of the x components plus the product of the y components and the product of the z components. That should give us this answer 62. And then also solve for the um, magnitudes of the distance vectors, RAB and RAC, which are this one, and use those information to compute for the angle. So this one came from the formula for getting the dot product using the coordinate system and feed that here or feed it there to get the angle. So that should give us this answer, which is 53.6. Um, for the last requirement, here we are asked to determine the component of the vector RAB along the vector RAC. So again, we compute for the dot product of RAB with the unit vector that is in the same direction as RAC. So that should give us the a scalar answer. So that would be actually this length here, and associate that answer with the unit vector. So this is really a two-step process. First, we get this dot product, and then we get the unit vector of RAC. So well, I combine them and use this formula instead. But you could what we could have done is also first get the dot product and then get the unit vector of RAC. And that should give us this answer here. In this example, we have again 3 points in space, A, B, and C. So first question is the cross product, RAB cross RAC. The area that is created by the 3 points in space, so that is a triangle. And the last requirement is the unit vector that is perpendicular to the plane of the triangle. So for the first question, to get the cross product RAB cross RAC, first we need to get the distance vectors RAB and RAC, and then compute for the cross product. So using the formula that we have for the cross product, where the vectors are expressed in their component vectors. So this is our answer for the first question. Now to get the area of the triangle, so let me draw here a triangle. So let's say this is point A, here is point B, and say this is point C here. So this is let's say RAB. Okay, so this is RAB, and this is AC. So the magnitude of the cross product, if we get the magnitude of the cross product, that would give us the area of the parallelogram created by the two distance vectors. So this would be the parallelogram created, and we're only after with the area of the triangle, which is really this area here, which is actually half of the area of the parallelogram. So so what we need to do is compute for the area of the parallelogram, get half of that, and that will give us this answer. Um, so take note, if we get the cross product RAB, RAC, that should give us a vector that is in this direction. Okay, so this would be uh, the cross product. So this is RAB cross RAC. So to get a unit vector, so we're answering here letter C. To get the unit vector of to get a unit vector that has the same direction as this, so we take the cross product and divide that with the length of or the magnitude of that cross product, and that should give us this answer here. Now, going back to the area, we could have get the area of these two distance vectors. We could have used RBA and RBC, and that should give us an area which is this one, and half of that also should yield the same answer. Half of the area of that parallelogram should also give us the same answer. So in this example, we have two vectors, E and F. Uh, so the first question is, what is the component of vector E along EF or along F? And B, what is the unit vector that is perpendicular to both A and F? So I won't give a complete answer, just give an overview of the process. So for A, we need to compute for E dot AF. Um, so to get AF, or the unit vector AF, which is a unit vector the same as the direction of the vector F, we need to get this one. And for letter B, to get a unit vector perpendicular to E and F, well, we need to solve first for the cross product E cross F and divide that result with the magnitude, with its magnitude, or we could do the reverse F cross E and divide it by the magnitude of, well, we could have used here F cross E magnitude, but it doesn't really make a difference if we use the magnitude E cross F. That should give us the same answer. For this example, we have 3 points in space, P sub 1, P sub 2, and P sub 3. And the question is if these 3 points lie on a straight line. So to answer this, so we have, say, 3 points, P1, P2, and P3. To prove that they lie in a straight line, we need to determine if the cross product of any of the distance vectors between any 2 points is a 0. So let's say this is the distance vector P1, P2. This is another distance vector P2, P3. So so we can actually draw them side by side. So this is our P1, P2, and let's say this is our P2, P3. So these two distance vectors are parallel if their cross product will yield a 0 answer. Because take note that in getting the cross product, this one, take note that this is also the product of their magnitudes times the sine of the angle between them. Okay, and since they are in parallel, the angle between them would be a 0, and that should give us a 0 answer. So all we need to prove is if whether the cross product will give us a 0, and that would mean that these 3 points here should lie on a straight line. So doing that, first we need to get the distance vectors P1, P2, and P2, P3. And so we have the answer here. And get the cross product P1, P2 cross P2, P3. And that should give us this one. It is actually a 0. And that would only mean that the 3 points are in a straight line. In this last example, we have 3 vectors, A, B, and C. And we are to prove whether these 3 vectors corresponds to the sides of a triangle. We also need to prove if the triangle is a right triangle and also calculate the area of the triangle. So to prove that the sides of the triangle are corresponds to these 3 vectors, we need to prove that the magnitude of A cross B must equal A cross C, because if they are the sides of the triangle, these 2 magnitudes must be equal, because both of them are the area of the parallelogram, and both must be equal. So to do this, first we need to compute for A cross B, and that should give us this answer. And getting the magnitude, uh, we should get this one. And also we get uh, A cross C, and that should give us also the same answer. And therefore, these vectors must correspond to the sides of a triangle. So let me illustrate that graphically. So let's say we have here the vectors forming the triangle. So A cross C must yield this area, the shaded area here. And let's say I move the vector B to coincide with the tail of vector A and C. So if I do an A cross B, that should give me this area here, and that area should be the same as the one above, because take note that this area here is the same as this area here, and this area here, which is also equal to the area here, is the same as this area here. So so since we got the same answer, uh, they should form the sides of the triangle. For the next question, whether the triangle is a right triangle, so we need to check if any of the dot product of the following, A dot B, A dot C, A dot or B dot C, will give us a zero answer. Because if any of these dot products will give us a zero answer, that would mean that the two vectors are perpendicular, and we know that the dot product is the product of the magnitudes times the cosine of the angle. So if they are perpendicular, the cosine must be at zero, because cosine 90 is a zero. So all we need to do is to check each of the dot products. So for A dot B, well, we didn't get a zero. For A dot C, not a zero. B dot C, also not a zero. So therefore, this triangle is not a right triangle. So that's it for the Cartesian coordinate system, and on our next video we will explore other coordinate systems and use them to manipulate vectors as well. So on our next video we'll be tackling the cylindrical coordinate systems and the spherical coordinate systems.